Welcome to this walkthrough of LeetCode problem number 1596, the most frequent subtree sum. In this session, we'll explore how to compute subtree sums within a binary tree and derive the most frequent values. Let's dive in and uncover the best possible solution for this problem. In this problem, we are working with a binary tree, and the goal is to determine the most frequent subtree sums. A subtree sum is defined as the total sum of all node values in a subtree, including the value of the root node of that subtree. For example, if you have a node and all its descendants, the sum of their values would be the subtree sum for that node. The task is to calculate these sums for all nodes in the tree and determine which sums occur most frequently. If there are multiple sums with the highest frequency, we return all of them in any order. The input will be the root of the binary tree, which is represented as a tree node object, and the output will be a list of integers representing the most frequent subtree sums. To understand the problem better, let's look at some examples. In the first example, we have a binary tree with the root node valued at 5, and it has two children, 2 on the left and -3 on the right. To calculate the subtree sums, we start with each node. The subtree rooted at node 5 has a sum of 5 plus 2 plus -3, which equals 4. The subtree rooted at node 2 has a sum of just 2, and the subtree rooted at node -3 has a sum of -3. Since all these sums occur only once, the output is a list containing all of them, 2, -3, 4. This demonstrates that when sums have the same frequency, we include all of them in any order. Now, consider another example where the binary tree has a root node valued at 5, with children 2 and -5. For this tree, the subtree rooted at node 5 has a sum of 5 plus 2 plus -5, which equals 2. The subtree rooted at node 2 has a sum of 2, and the subtree rooted at node -5 has a sum of -5. Here, the sum 2 occurs twice, while -5 occurs only once. As a result, the most frequent subtree sum is 2, and the output is 2. This example highlights how the frequency of sums determines the result. Finally, let's look at a simple example with just a single node. If the binary tree consists of only one node with a value of 1, the subtree sum is simply the value of that node, which is 1. Since there is only one subtree and one sum, the output is 1. To summarize, the constraints of the problem specify that the tree can have up to 10,000 nodes, and node values can range from -100,000 to 100,000. The algorithm must handle edge cases such as single-node trees, trees with nodes having identical values, negative node values, and very large trees efficiently to ensure it performs within the given limits. To solve the problem of finding the most frequent subtree sum in a binary tree, we start by understanding the key tasks involved, computing the sum of all nodes in every subtree, and then identifying which of these sums occurs most frequently. One approach we considered is the brute force method. The intuition behind this is straightforward. At each node in the tree, we calculate the sum of all nodes in its subtree by traversing the subtree entirely. To keep track of how many times each sum appears, we maintain a frequency map. However, the challenge with this method lies in its inefficiency. Since subtree sums are calculated repeatedly for overlapping subtrees, the time complexity becomes n squared for a tree with n nodes. While this approach is simple to implement, it becomes impractical for larger trees due to the redundant calculations involved. A more efficient solution is the optimized approach using post-order traversal combined with memoization. Post-order traversal processes the left and right subtrees of a node before the node itself, ensuring that subtree sums are calculated only once. During this traversal, we compute the sum of the current subtree and store it in a frequency map, which tracks how often each sum occurs. This eliminates redundancy because the sums for all subtrees are reused as needed. The implementation involves a depth-first search where we compute subtree sums recursively. After the traversal, the frequency map allows us to quickly determine the most frequent sums. This approach has a time complexity of n, as we visit each node only once, and a space complexity of n, to store the recursion stack and the frequency map. While this method requires a solid understanding of recursive tree traversal, it is both efficient and elegant. Another alternative is level order traversal, which computes subtree sums iteratively while maintaining a frequency map. This avoids recursion but involves additional bookkeeping to manage parent-child relationships and track intermediate sums. Although it has the same n complexity, the iterative approach can be harder to implement and manage. Among the approaches discussed, the optimized post-order traversal with memoization stands out as the most effective strategy for solving this problem. Its efficiency is a key advantage, with a time complexity of O(n) that makes it well suited for handling large inputs. The recursive nature of the traversal aligns naturally with the problem's requirements, making the implementation clear and intuitive. Additionally, this approach avoids redundant calculations by ensuring that each subtree sum is computed exactly once, leveraging the overlapping subproblem structure. While recursion does introduce a space cost of O(h), where h is the height of the tree, this is typically manageable, especially for balanced trees. Compared to the iterative alternative, which adds complexity, the post-order method strikes an ideal balance between simplicity and performance. The insights that make this approach particularly powerful include the bottom-up calculation of subtree sums, the use of a frequency map to efficiently track sums, and the ability to solve the problem in a single traversal. The optimized post-order traversal with memoization was chosen over the other approaches for several reasons. The brute force method, while simple, is computationally expensive and becomes impractical as the input size grows. On the other hand, the iterative approach using level-order traversal, though feasible, introduces unnecessary complexity without offering any significant performance gains. By contrast, the post-order traversal approach provides the right combination of efficiency, simplicity, and clarity. It minimizes redundant work, aligns naturally with how subtree sums are structured, and is straightforward to implement for those familiar with recursive tree algorithms. This balance of trade-offs makes it the ideal solution for tackling this problem effectively. To solve this problem, we need to compute the sum of all nodes in every subtree of a given binary tree. The goal is to identify the subtree sum or sums that occur most frequently. If multiple sums have the same highest frequency, we return all of them in any order. Let's break this down further. First, the subtree sum of a node is defined as the sum of all values in the subtree rooted at that node, including the node's own value. For instance, if we have a tree with root value 5 and its left and right children are 2 and minus 3 respectively, the subtree sum for the root is calculated as 5 plus 2 plus minus 3, which equals 4. The approach we use to solve this is recursive post-order traversal. This method ensures we compute the sums of a node's left and right subtrees before calculating the node's own subtree sum. To track how frequently each subtree sum appears, we use a dictionary where the keys are the subtree sums and the values are their frequencies. For example, if the subtree sums are 4, 2, minus 3, and 4, the dictionary will eventually look like 4 appearing twice, while 2 and minus 3 appear once each. Now, let's define the recursive function that will calculate these subtree sums. We create a helper function called DFS which takes a node as input. The base case is simple: if the node is null, we return 0, as a null node contributes nothing to the subtree sum. For the recursive case, we first compute the sum of the left subtree by calling DFS on the node's left child. Then, we compute the sum of the right subtree by calling DFS on the node's right child. Once we have these values, we calculate the current subtree sum by adding the left sum, the right sum, and the value of the current node. We then update the frequency of the current subtree sum in the dictionary. Finally, we return the current subtree sum to the parent node. After calculating the sums for all nodes, we can iterate through the dictionary to find the maximum frequency. Any subtree sums that have this maximum frequency are added to the result. Some edge cases to consider include a single node tree, where the subtree sum is simply the value of the node, or trees where all nodes have the same value, which may result in tight frequencies. Additionally, since the tree may contain negative values, the algorithm should handle these correctly. This approach relies on several key insights. First, post-order traversal is essential because it ensures that we compute the subtree sums for a node's children before calculating the sum for the node itself. This dependency is crucial for the correctness of the algorithm. Second, using a dictionary to track the frequency of each subtree sum allows us to efficiently store and access these values without recomputation. This eliminates unnecessary comparisons and ensures the algorithm runs efficiently. Speaking of efficiency, the time complexity of this approach is O(n), where n is the number of nodes in the tree. Each node is visited exactly once, and dictionary operations like insertion and updating are O(1) on average. The space complexity is also O(n). This accounts for the dictionary, which can store up to n unique subtree sums, and the recursion stack, which has a depth proportional to the height of the tree. In the worst case of a skewed tree, this depth could be O(n). As for the data structures, we use a binary tree represented by nodes with value, left, and right attributes, a dictionary for frequency tracking, and the implicit recursion stack during traversal. Let's walk through an example to see how the algorithm works in practice. Consider a binary tree with root value 5, a left child with value 2, and a right child with value -3. We start by calculating the subtree sum for the left child, which has value 2. Since both its left and right children are null, their subtree sums are 0. The subtree sum for this node is therefore 2 plus 0, which equals 2. We update our dictionary to reflect this sum, setting the frequency of 2 to 1. Next, we move to the right child of the root, which has a value of -3. Just like before, its left and right children are null, so their subtree sums are 0. The subtree sum for this node is -3 plus 0, resulting in -3. We update the dictionary again, adding -3 with a frequency of 1. Now we are ready to compute the subtree sum for the root node. For the root node, we already have the subtree sums of its children, 2 from the left child and -3 from the right child. Adding these to the root's own value of 5 gives us a total subtree sum of 4. We update the dictionary one last time, adding 4 with a frequency of 1. At this point, the dictionary contains 3 entries, 2, -3, and 4, each with a frequency of 1. To find the most frequent subtree sums, we look for the maximum frequency in the dictionary. Since all sums have the same frequency of 1, we return all of them as the result. The order of the sums in the output doesn't matter, so the result could be 2, -3, 4, or any permutation of these values. The time complexity here remains O(n), since each node is processed once, and the space complexity is O(n), for both the dictionary and the recursion stack. This ensures the algorithm is efficient even for large trees. Finally, let's summarize the pseudocode for this solution. We start by defining the helper function DFS, which calculates the subtree sums recursively. If the current node is null, we return 0. Otherwise, we compute the left and right subtree sums by calling DFS on the node's children. We then calculate the current subtree sum by adding these values to the node's value. This sum is added to our dictionary, where we increment its frequency. The current subtree sum is then returned to the parent node. After defining DFS, we initialize the frequency dictionary and start the traversal from the root. Once all subtree sums are computed, we find the highest frequency in the dictionary. Finally, we return all sums with this maximum frequency. This algorithm leverages post-order traversal and a frequency dictionary to efficiently compute and identify the most frequent subtree sums. Here, we begin by importing the default dict module from the collections library, which will help us maintain a frequency map for subtree sums. Within the solution class, we define the find_frequent_treesum method, which takes the root of a binary tree as its input. To calculate the subtree sums, a helper function calculate_subtree_sum is defined. This function is a recursive method that processes each node in the tree. If the current node is null, it simply returns 0, as there is no contribution to the sum. Otherwise, it recursively calculates the sums of the left and right subtrees using the node.left and node.right pointers. Once the left and right subtree sums are computed, the current node's subtree sum is calculated by adding the node's value to these two sums. This value represents the total sum of all nodes in the subtree rooted at the current node. The frequency map is then updated to increment the count for this particular subtree sum. Finally, the function returns the calculated subtree sum for the current node. Before invoking this helper function, we handle the edge case where the root is null by immediately returning an empty list, as there are no subtree sums to calculate. At this point, we initialize the frequency dictionary to store the counts of all subtree sums as we traverse through the tree. Next, we call the calculate_subtree_sum function, starting from the root of the tree. This ensures that every node in the tree is processed, and all subtree sums are calculated and recorded in the frequency map. Once all the subtree sums are computed, we determine the maximum frequency by finding the highest value in the frequency dictionary. This represents the most common occurrence of any subtree sum. Finally, we construct the result by iterating over the dictionary and collecting all subtree sums whose frequency matches this maximum value. These are the sums that occur most frequently in the tree. The method then returns this list of sums, providing the desired output. This implementation efficiently handles the computation by leveraging recursion and a dictionary, ensuring that we process each node only once and store the necessary frequency data for quick retrieval. Here, we start by defining the treeNode class, which represents the structure of a binary tree node. Each node contains a value, a left child, and a right child. We then define the solution class, where the main logic for solving the problem resides. The method findFrequentTreeSum takes the root of the binary tree as input and returns an array of the most frequent subtree sums. First, we handle the edge case where the root is null by returning an empty array. Next, we create a hash map called FrequencyMap to store the frequency of each subtree sum. The helper method calculateSubtreeSum is called to compute the subtree sums recursively, and their frequencies are stored in the map. Once all sums are calculated, we determine the maximum frequency by using the collections.max method on the values of the frequency map. Now, to find all subtree sums that occur with this maximum frequency, we create a list called result. We iterate through each entry in the frequency map, and if the frequency matches the maximum frequency, we add the corresponding subtree sum to the result list. Finally, we convert this list into an integer array and return it. The helper method calculateSubtreeSum is defined below. It takes a tree node and the frequency map as inputs. If the node is null, it returns a sum of 0. Otherwise, it recursively calculates the subtree sums for the left and right children, adds the current node's value to these sums, and updates the frequency map with the new subtree sum. This recursive process ensures that every subtree sum in the tree is calculated and recorded. The method then returns the subtree sum for the current node, enabling the recursion to continue building sums up the tree. Let's start with a simple tree. The root is 5, and it has 2 children, 2 on the left and -3 on the right. We begin by calculating the subtree sum for the root node, which means we first need to calculate the subtree sums for its children. For the left child, 2, since it doesn't have any children, both its left and right subtree sums are 0. So, the subtree sum for node 2 is simply 2 plus 0 plus 0, which equals 2. We then add this sum to our frequency map, initializing it with 2, 1. Next, for the right child, -3, the process is similar. Both of its children are also none and contribute 0 to its subtree sum. So, for node -3, the calculation is -3 plus 0, which equals -3. We add this to our frequency map, updating it to 2, 1, -3, 1. Finally, we calculate the subtree sum for the root node 5. Adding its value to the sums of its left and right subtrees, we get 5 plus 2 plus -3, which equals 4. Updating the frequency map again, we now have 2, 1, -3, 1, 4, 1. Since all sums have the same frequency of 1, the result is all the subtree sums, 2, -3, 4. Now let's look at a tree where some subtree sums are repeated. Here, the root is again 5, and its children are 2 on the left and -5 on the right. Starting with the left child, 2, it has no children, so its subtree sum is 2 plus 0, which equals 2. We add this to the frequency map, giving us 2, 1. For the right child, -5, the calculation is similar, -5 plus 0 equals -5, and the frequency map becomes 2, 1, -5, 1. Now, for the root node 5, its subtree sum is 5 plus the left subtree sum of 2, plus the right subtree sum of -5. This gives us 5 plus 2 -5, which equals 2. Adding this to the frequency map, we notice that the frequency of 2 increases to 2, making the updated map 2, 2, -5, 1. The highest frequency here is 2, so the output is the subtree sum with that frequency, which is 2. Finally, let's consider the simplest case, a tree with just one node, 1, since this node has no children, both its left and right subtree sums are 0. The total subtree sum for this single node is therefore 1 plus 0, which equals 1. We add this to the frequency map, resulting in 1, 1. With the maximum frequency being 1, the only subtree sum that qualifies is 1. This highlights how the approach works even for the smallest trees, consistently determining the most frequent subtree sum. Here, we analyze the time complexity of our solution. The first step is the recursive traversal of the binary tree. Each node is visited exactly once in the calculate_subtree_sum function, where we compute the sum of its left and right subtrees along with its own value. For a tree with n nodes, this traversal takes n time. Next, for each node, we update the frequency of its subtree sum in the frequency dictionary. Since updating a dictionary entry is an O(1) operation, this step also takes n time in total for all nodes. Finally, we determine the maximum frequency from the frequency dictionary. The number of unique subtree sums is bounded by the number of nodes, so this operation takes n time as well. Combining these steps, the total time complexity of the solution is n. Now, we look at the final step of the time complexity analysis, collecting all subtree sums with the maximum frequency. This involves iterating over the dictionary to gather the relevant sums. In the worst case, this operation takes n time, as there can be up to n unique subtree sums in the dictionary. With all these steps combined, the overall time complexity remains n. Next, we turn to space complexity. The first factor is the space used by the recursive call stack. The depth of the stack is proportional to the height of the binary tree. For a worst-case scenario, such as a skewed tree, the height can be n, resulting in n space usage. In a balanced tree, the height is log n, making the space usage for the call stack significantly smaller. Another major contributor to space complexity is the frequency dictionary. In the worst case, where each node has a unique subtree sum, the dictionary can grow to have n entries, requiring n space. Another factor in the space complexity is the output list, which stores the subtree sums with the maximum frequency. In the worst case, all n nodes may have the same subtree sum, resulting in an output list of size n. Combining all these factors, the overall space complexity of the solution is n, in the worst case, primarily due to the dictionary and the recursive call stack. To contrast this with a naive approach, if we were to calculate the subtree sums for each node independently, it would lead to significant redundancy. For each node, we would recursively compute the sum of its subtree, resulting in a time complexity of n squared, for a tree with n nodes. The optimized solution avoids this redundancy by calculating all subtree sums in a single traversal and leveraging a dictionary to store intermediate results. Finally, let's summarize the best, average, and worst-case scenarios. In the best case, for a perfectly balanced tree, the depth of the recursive call stack is log n. However, the overall time and space complexities remain n, driven by the dictionary and output list. For the average case, with a typical binary tree, the complexities also stay n, for both time and space. In the worst case, for a skew tree, the recursive call stack depth grows to n, but the overall time and space complexities are still n. Mathematically, this efficiency is justified because each node is visited exactly once during the traversal, contributing n time. Dictionary operations, such as insertion and lookup, are O(1), ensuring no redundant computation. The dictionary and call stack together contribute n space, resulting in an overall space complexity of n. When solving this problem, there are a few common mistakes to watch out for. First, subtree sums can be negative or zero depending on the values of the nodes, so it's essential not to assume that all sums will be positive. Failing to handle these cases can lead to incorrect results. Another frequent issue is using the wrong tree traversal method. For this problem, post-ordered DFS is critical because it ensures each subtree is fully processed before calculating its parent's sum. If you were to use BFS or another traversal method, you might compute sums incorrectly. Additionally, it's important to account for edge cases, such as a tree with only one node or an empty tree. These are common scenarios that can cause unexpected errors if not explicitly tested. Inefficient frequency calculation is another pitfall. Using a list instead of a dictionary or collections counter can slow down lookups and updates, especially for large trees. Lastly, remember that the problem requires handling ties for the most frequent sum. If you return only one sum instead of all tied sums, your solution will fail to meet the requirements. Now, let's focus on some insights that can be particularly helpful during interviews. A key point to emphasize is that post-order traversal is the most logical approach for this problem. It allows you to calculate subtree sums efficiently by ensuring all child nodes are processed before their parent. Another important strategy is to use a dictionary or hash map to track frequency counts. This data structure makes lookups and updates quick, which keeps the solution efficient. As you explain your approach, be sure to communicate how you handle edge cases, such as empty trees, single-node trees, and negative sums. This demonstrates thoroughness and critical thinking. If asked about optimizing for large inputs, you can discuss the efficiency of your solution, which should have a time complexity of O(n) and a space complexity of O(n) to account for both the recursion stack and the frequency map. Additionally, it might be helpful to mention related problems, such as pathsum 3, which involves counting paths with specific sums, or binary tree maximum path sum, which focuses on maximizing path values. These problems can provide further context and demonstrate your ability to draw connections between similar challenges. There are also some alternative approaches to consider, though they may not be optimal for this specific problem. One straightforward method is the brute force approach, where you calculate the sum of every subtree for each node using a top-down traversal. While this is simple to implement, it leads to a time complexity of O(n) squared, because each subtree sum is recalculated multiple times. A more efficient alternative, if subtree sums are needed for multiple queries, is to use memoization. By storing the sums in a cache, you can avoid recomputation, which saves time at the cost of some additional space overhead. Another option is to use an iterative postorder traversal instead of a recursive one. This approach avoids the risk of stack overflow for very deep trees, but it's more complex to implement and can feel less intuitive for this problem. While these techniques can be valuable in certain contexts, the recursive postorder DFS paired with a hash map for frequency counts remains the most efficient and straightforward solution for solving the most frequent subtree sum. Great work! We've successfully broken down and solved LeetCode problem number 1596, the most frequent subtree sum. Remember the importance of hash maps for frequency tracking and how DFS simplifies tree traversal. Thank you for joining, and I hope to see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!